screen
looks
when
very
it's on.
familiar.
Yep.
It's okay if I put it in the same pocket as the cell phone. Just usually glitch out. Let's see. All right. Let's just see this. That's about it.
Do you want to write something first, or should I go ahead and introduce you?
Either way.
Why don't I just...
Depending on the time.
Yeah, let's just time.
That's just time.
Okay. Good morning, everybody. Hope everyone's doing well. So we are glad to begin another lecture series. Thomas Dumitrescu from UCLA is going to be telling us about generalized symmetries and quantum field theory. Thomas.
Thank you very much. Can you guys hear me? All right. Not yet. 1, 2, 3. 1, 2, 3. Is it on? No, it's on.
Maybe make it a little more central.
Yeah. How about now? Better? All right. All right, so thank you, Oliver. Thank you to all the organizers for putting together a beautiful school and for inviting me. So this is week 2, so I'm going to be telling you about some things that build on what you heard about in week 1. And the title that the organizers assigned to me was Generalized Symmetries in Quantum Field Theory. And this is a very generous and unrealistically broad title, so I'm going to do my best to narrow down the scope a little bit, but nevertheless, this is roughly speaking what I'll be talking about. So just the obvious reminder, of course, I'm very happy to take questions at any time. I hope you'll interrupt whenever something is unclear. And at various points, I might assign a little exercise or a little something that you can work out for yourself as well. And we'll take it from here. All right. Good. So before I tell you exactly how much I want to narrow the scope, let me first talk a little bit about ungeneralized symmetries. So in other words, ordinary, familiar symmetries, things that have now come to be called zero-form symmetries. And there are many kinds of such symmetries. We encounter many of them in undergraduate physics and in quantum field theory. And especially in the case of continuous symmetries, we have the additional richness and the additional handle of conserved currents. For example, if you have a U1 symmetry, maybe you have a conserved neutral current J mu, which is a vector, a conserved vector. And if you're talking about Lorentz invariant theories, which I'll be doing exclusively, then you also have Poincare symmetry or Euclidean invariant. There's a conserved symmetric stress tensor. And these objects we study all the time. And of course, there are also many interesting examples of discrete symmetries, both internal and space-time symmetries, for which there are no such currents, but nevertheless, we can say much about them. And I just wanted to make a kind of short list of things that we usually do with such symmetries. To jog your memory, hopefully these are ready. And if something is very new, then please interrupt, and I'll say more about it. So, of course, the main claim to favor symmetries, and why we're interested in them is that they imply non-trivial relations between interesting physical measurable quantities. And so they constrain the theory. This is the thing that should always be in the front of your mind. And then there are many layers of sophistications that go on top of that, especially when you graduate from quantum mechanics to quantum field theory. They're rigid under a normalization group flow. I can't talk about this. This is the easiest things to track from the UV to the IR in an interacting and potentially non-solvable. They can be vacuum, or they can be spontaneously broken, and that means that the corresponding charges don't annihilate the vacuum, but that doesn't mean that they're not interesting. They have interesting consequences, even if they're spontaneously broken. For example, in this case, they might lead to Nambu-Goldstone bosons. Another thing that symmetries are great for, both in particle physics and matter physics, is to characterize phases. Phases of quantum field theory, phases of statistical systems. And in the case of ordinary symmetries, this is the Landau paradigm for phases and phase transition. So if the symmetry of the model is realized in different ways in the deep infrared in two different scenarios, that means that those two scenarios cannot belong to the same phase. For example, symmetry breaking pattern and the number of Goldstone bosons, then continuously to the other, there has to be a phase transition in between. All right. So another thing we can do, and that is always good advice, is to consider coupling your symmetries to background fields. You can couple any operator to a background field, but for a symmetry, it's a special background field because it's a background gauge field. And so, for example, you can couple J and U to a background U1 gauge field, or you can couple the stress tensor to a background metric, and we'll see more sophisticated things that can be coupled to other kinds of background gauge fields, both continuous and discrete. One of the reasons it's a good idea to do is because you might be interested in gauging these symmetries, and then you have to figure out how to promote those gauge fields to dynamical ones and do the path integral over them. Alternatively, you might want to keep them global, but you might be interested in possibilities they have, and they're also the background fields can help you. Right. And of course, if there are anomalies, then they have to satisfy matching conditions. Again, anomalies are properties of a symmetry or of a theory that are rigid under G-flow. All right. And if there is an anomaly, then the thing that cannot happen is that the theory is just completely gapped and trivial in the IR. So we'll review that in detail, but I'm sure you've seen examples of it already. Any questions so far? All right. So a couple of other very broad comments. Global symmetries are great if they are there and they're exact, but they're almost as great if they're only approximately there. This is very important. For example, in QCD, we learn a lot from symmetry, even with us break that symmetry a little bit. This is a general feature of global symmetries over and over again. This is different from gauge symmetries, by the way, because gauge symmetries, not symmetries at all, have to necessarily be exact. All right. And the other thing, important, falls into the same bucket, is that symmetries can be what in particle physics is called accidental, or what in condensed matter physics is called. So they're not really theory, but they're good approximate symmetries at long distances. And a particle physics example is baryon and lepton number in the standard model, which is violated by higher dimensional operators. Good. And of course, we all believe that in quantum gravity, all symmetries are of this kind. All symmetries should be accidental. The discussion, the interesting discussion that people are having is how dramatic the violation coming from quantum gravity should be. Okay, so all of this is just to reinforce your memory about the fact that symmetries are awesome. They're there, they're very useful. There are lots of things you can do about it. Obvious that if you have such a useful machine, you would want to generalize it in various ways. So in other words, you want to find new kinds of symmetries that are just as good and just as useful. And something that people thought about recently. People have been trying to do this for years, maybe hundreds of years, thousands of years, and attempts to do that. One of the oldest ones in the sort of past century is to try to generalize these kind of symmetries, continuous symmetries like this, with currents from the case of a vector current with one index to the stress tensor with two indices to something that has more than two indices and is nevertheless conserved. So something like something with three indices, for example, and something that's symmetric in those three indices, right? Just like the stress tensor is symmetric to indices. These are interesting symmetries. They're higher spin symmetries, and they're very, very constrained. So there's the famous Coleman-Mandula theorem, which tells you that essentially more than two space-time dimensions, the only theories that have such symmetries are free, at least at the level of their S matrix. There are interesting loopholes. Loopholes to the Mandula theorem. Two of them probably can. One is super, and the other is conformal symmetry, where you can sort of squeak in between these two, in a sense. Very good. The other kind of orthogonal generalization involves what is known as higher form symmetries. So this is generalization number one. These are called higher spin symmetries. They're higher spin because the current is symmetric. There's then the other direction, which goes into higher forms. And these involve currents that have multiple indices, but are anti-symmetric in those indices. And because of the so we'll study such examples, and because of the anti-symmetry of the currents, they do not act on particles. They do not act on the S matrix, and this is how they avoid the Coleman-Mandula argument. But they act on something, and they turn out to act on extended objects. Dynamical strings, for example, if your theory has dynamical strings. Not operators, like line operators. In fact, the example that we'll study the most is the case of one-form symmetries, where this J mu nu only has two anti-symmetric tensor indices, and that is the case that most naturally arises in gauge theory all over the place. Time dimension.
Can you just clarify why the anti-symmetry makes them acting on non-local operators?
So the more obvious once I write on the corresponding charges. Get charges for these gadgets, you integrate them over all of space. And that means that if you have a particle sitting in space, the integral that calculates the charge picks up on the charge of that particle. These things, in order to compute their charge, you naturally have to integrate it over a lower dimensional subspace. For example, for a one-form, you just integrate over a two-dimensional plane inside three-dimensional space. We'll see an example in 10 minutes. Now, because for a lower dimensional space, you can evade point particles by sliding the symmetric surface around them. So this is essentially a topological argument for why these don't count. Yeah. Other questions? All right. Very good. So one other comment that I want to make is that both these symmetries and these symmetries also have yet another kind of generalization. You generalize the familiar group structure that you typically associate with symmetry to things that are not quite groups, things that have more general. Those are the so-called non-invertible or higher category symmetries, and you might have already heard about them, and I'm sure you'll hear more about them. And so I will not. The thing that I will discuss is the following. I will discuss higher form symmetry, especially one-form symmetry, and their interplay with ordinary symmetries, which can be more or less involved. And the natural setting, as I mentioned for this, is gauge theories, because gauge theories naturally give rise to one-form symmetries. So the way that I wanted to limit the scope is, first of all, restrict to gauge theories. And there are lots of gauge theories and lots of dimensions. They're interesting and rich. And so I'm going to restrict myself even more and stick to 4D gauge theories. 4D being the total Euclidean space-time dimension. I will essentially always work in Euclidean signature. This has some advantages and some disadvantages, as you'll see. So when I say 4D, I mean 3+1 dimensional spacetime. This is the natural setting for CD and for particle physics and for many other good things. All right. And what I would like to do is to study I was going to say a sequence of examples, but it's going to be a finite list of examples of increasing complexity in this category of 4D gauge theories that have not these, but these kind of global symmetries, also ordinary ones. And I want to illustrate, in as much as I can in the time given, how to use the symmetries to learn about the dynamics of these theories and to really show these symmetries in action. In other words, these are not just something that we cook up because they're associated with a nice formalism. They actually have teeth, and they help you understand something. So hopefully we'll see that, at least to some degree. All right. So today we're going to start simplest of all of these examples, the simplest four-dimensional gauge theory, which is, well, that's a matter of debate. But at least to me, the simplest four-dimensional gauge theory is free Maxwell theory, free abelian gauge theory. And so we'll immediately see an example of this kind of conservation law there. And essentially all the features of generalized symmetries that will come later can be illustrated using that example. So there are, I'm sure, many other people who will mention Maxwell theory in their lectures. Maybe Greg will mention it. I'm sure others will too. That's excellent. If more than one person mentions it, it probably means that it's important. And the way you should think about Maxwell theory in 4 dimensions is that it's sort of, Maxwell theory is to one-form symmetries in 4 dimensions as the C=1 compact boson is to 0-form symmetries in 2 dimensions. You'll see many parallels. And just like many lecturers last week discussed the compact boson in all its glory, I'm sure that many of us will discuss Maxwell theory in all its glory. So hopefully that will lead to some kind of enhanced understanding. All right. Right. So as I mentioned, I'll be in Euclidean. So we'll start with spacetime being Euclidean R4. And I'll only discuss theories that are Lorentz invariant and Lorentzian signature and that are suitably Euclidean continued. Now, because I'm studying analytically continued Lorentz invariant theories, I'm going to allow myself a certain sloppiness, which is standard in this business. I'm not going to distinguish between defects, operators, insertions, and so forth. In principle, I'm doing Euclidean statistical mechanics, so I as an intro to the path integral. There are no Hilbert spaces, there are no operators. But of course, you know that when you rotate back, many of these things become operators. So I'm going to use terminology interchangeably. It's OK to be sloppy about it in this context, because in the relativistically invariant context, essentially every operator and every defect has a dual role as either something acting on a Hilbert space or something that you can insert as a defect. In non-Lorentz invariant theories, one needs to be much more careful, because these things are not necessarily the same. All right. All right, let's start with Maxwell theory. The action in flat spacetime, written in terms of the gauge field, looks like this. I'm going to write it in terms of the field strength, and here M4 is spacetime. So let me make some comments. There's no clock that I can see. Are you going to? Oh, there is. Can you give me some warning when the time comes?
Sure. What do you want?
15 minutes? Yeah. 15 minutes. Thank you. Right. So we're going to be writing lots of differential forms and related objects. So anytime you see a superscript like that, it means the form degree of whatever I'm writing. So here, for example, A1 is the gauge field, thought of as a 1 form. F is its field strength, dA. And of course, because F is 0, this is the Bianchi identity. This is example number 1 of our conservation law, as I'll flesh out in a second. The other Maxwell equation comes from varying little a. So force it in sight. And let's see, what else do I want to say? So A1 is a standard U1 gauge field, or U1 connection, meaning we identify A's that differ by a gauge transformation, and that the gauge field is a U1 connection is related to the statement that the gauge parameter lambda is not necessarily a well-defined function of space-time, but is circle valued, so that it can jump by 2 pi n. If you wish, it's like the compact boson in 2D, except that the compact boson was a physical object, and here lambda is the gauge parameter. Good. Now, the old Dirac argument from quantum mechanics links the periodicity of lambda with the allowed fluxes for F. Okay, so once I've chosen lambda to satisfy this, then the fluxes of F are normalized in a particular way. If I compute the flux of F over a given 2-cycle sigma 2, it has to be in 2 pi times the integers. In this case of the sphere, which is the case that Dirac studied, you cut open the sphere along its equator, and then you get a gauge transformation, which has to wind around like this. And the winding number of the gauge transformation gives you the flux of F. There are more sophisticated ways of saying almost anything that I'm saying. Maybe you'll hear about it from somebody else. All right. And when we study this theory, we do the path integral of A modulo gauge transformations. So we're modding out by these gauge transformations. That means we're path integrating over gauge orbits, distinct gauge of A. Now, one thing which is important, which is one of the first real analogies without any matter, the gauge coupling E here is meaningful. So you cannot just rescale F and get rid of E because of this quantization condition on the field strength. Okay? If E disappears from action, but it'll reappear as a modified quantization condition. So E is literally the analog of the radius of the compact boson. Meaningful, of course, also there. Very good. So before we study the generalized symmetries of Maxwell theory, let's make a short list of the ordinary. I already talked about space-time symmetries, right? Poincare symmetry with a conserved stress tensor. Here we have Euclidean signature. I'm making here a short list of the zero form. Here we're in Euclidean signature, so we have Euclidean SO4 and translation symmetry. With associated stress tensor. I'm not going to write that. Notice that I didn't include a theta angle in my theory. That makes the whole theory more interesting and more rich, but it also introduces complications, so I'm going to ignore it for now. That means that the theory also has time reversal and parity. In Euclidean signature, those two things are the same thing. They become a Euclidean reflection, R. And that Euclidean reflection enhances SO4 to O4. However, I will mostly not discuss time reversal symmetry in these lectures, except that special junction. All right. And then there's charge conjugation, which maps F to minus F, or if you wish, A to minus A, which is a Z2 non-spacetime symmetry. All right. And as I mentioned over here, it's a good idea to couple everything to background fields. So what are the suitable background fields for these symmetries? Well, here we have space-time symmetry, so we can put the theory on any suitably nice four-manifold M4. as long as we specify a metric. The Hodge star there implicitly depends on the metric. Of course, if you explicitly write it out in terms of tensors, you'll see that. The topology of M4 can be arbitrary. I will always take M4 to be oriented because I don't want to talk about time reversal. Since this theory actually has time reversal symmetry, you could also put it on non-oriented manifolds. And so you should think of these manifolds with their topology and their metric structure as providing background fields for the space-time symmetries. The global symmetry, of which this is the only one, couples to internal gauge fields. And so charge conjugation being a Z2 symmetry couples to some Z2 gauge field. All right. Any questions so far? Great. So the second analogy with the compact boson is that Maxwell theory has many equivalent presentations, just like the compact boson does. And some are more useful than others. One of the most useful ones is the one that you obtain by applying electric-magnetic duality to this theory, all right, or S duality. So let me go over here. This is analogous to the R to 1 over R duality of the compact boson. All right. So let me give a very quick derivation of S duality in the theory. We start with the action that I wrote over there. But instead of imposing the flux constraint on F and the flatness of F by trivializing F in terms of a connection A, I can equally well impose those constraints by a totally local and nice way by using a Lagrange multiplier. So I'm no longer going to think of F as dA. F is just an unconstrained two-form. And I'm going to impose the Bianchi identity by a Lagrange multiplier. So our action is now 1 over 2e squared F wedge star F plus a term involving F and a new field, which I'll call A tilde, via its field strength dA. A tilde is a Lagrange multiplier. That is supposed to enforce the Bianchi identity. And you see that the equation of motion of A tilde does that, because that just sets dF equal to 0. However, A tilde needs to do something more sophisticated. It also needs to restrict the fluxes of F to be in 2 pi z. And the way to do that is to take A tilde itself to be a U1 gauge field, which is also conventionally normalized the way I normalized A over there. So it itself has gauge transformations, which are different from the gauge transformations of A. They're dual magnetic gauge transformations. And the fluxes of A tilde are in 2 pi z. Let me write it explicitly as dA tilde. That's in 2 pi z. All right. So we've already decided that if you integrate over small fluctuations of A tilde, then that imposes the Bianchi identity. But what do the fluxes of A tilde do for you? If you sum over all the possible fluxes of A tilde, then this kind of term in the path integral will give you essentially a path integral representation of a delta function that sets the fluxes of F to be 2 pi times an integer. So doing the full path integral over A tilde, so doing dA tilde in the path integral restricts the fluxes of F to be in 2 pi z. So in other words, if you integrate out A tilde and you forget about it, then you recover the original presentation of the theory. And the way to get the dual presentation is to instead integrate out F and use A tilde as the new variable. So if you do that, right, the equation of motion for F viewed as an unconstrained two-form is easily obtained from this action. It's just, I'm going to write it like this. I over E squared star F is equal to 1 over 2 pi times F tilde, where F tilde is the dual field strength, the field strength of A tilde. The factor of I here is regrettable, but it is unavoidable in Euclidean signature. In Lorentzian signature, there's no I, but you're going to use the Lorentzian Hodge star, which has slightly different properties than the Euclidean Hodge star. So we're going to have to live with that I, since I chose to be Euclidean. Yeah? Sigma 2 is closed. Can you repeat that?
I've got something exact that I'm integrating over close to a cycle.
Here. It has to vanish if the question was, if I look at this formula, which is analogous to the flux quantization formula I started with in the other theory, and I'm integrating d of something, why am I not getting 0, since sigma 2 is a closed two-cycle? And that would be the case if this A here were a well-defined one-form. Then Stokes' theorem would tell you that this vanishes. But A is a gauge field, which shift by gauge transformations. So it's exactly the non-triviality of the U1 gauge transformations in the place where you would try to use Stokes' theorem that makes the fluxes non-zero. That's a very important thing, so thanks for asking. All right. As I said, in Lorentzian signature, you get the same formula, except with I replaced by, so I star is going to be the Lorentzian star. And interpreted in terms of usual component fields, this is the statement that E goes to B and B goes to minus E, which is the usual duality operation. All right. So we'll have much more to say about this equation, but for now, let me just use it to eliminate F from the action. And then I'll get the dual presentation of this theory that only depends on A tilde. I'll get S of A tilde. And you see that because of the gauge coupling here, the gauge coupling in the action is going to be modified. So if I rewrite the action for A tilde in terms of some new gauge coupling E tilde, and I write it as F tilde wedge star F tilde, then the dual gauge coupling, E tilde squared, is 4 pi squared divided by the original E squared. Right, and that just comes from solving for F as E squared over 2 pi and plugging back. So you see that modulo those 2 pi's, which come from my conventions, this is exactly like R going to 1 over R in the compact boson, where strong and weak coupling are exchanged. Now let me make a comment about the status of this S operation. For general values of E, the operation is not symmetry. It's a change in the presentation. You call it a duality, but a duality is a change in the presentation. Just tells you that some Lagrangian written in some way describes the same physics as some other Lagrangian written in some other way. However, at a special value of E, right, precisely the self-dual value of E, where E tilde is equal to E, that happens when E is equal to 2 pi, then the original Lagrangian and the new Lagrangian are actually the same. So the operation on the fields, even though it's complicated, does map the theory to itself. So it is a symmetry. So at self-dual point, S enhances to an actual symmetry of the theory. And one important comment about S is that it is not a Z2 symmetry. If you do S twice, you don't get back the identity. If you do it twice, then all the fields go to minus themselves. So you get charge conjugation instead. That's roughly because E goes to B and B goes to minus E. So S, when it is a symmetry, is actually a Z4 symmetry. The same applies to the compact boson at the self-dual point. All right, any questions about this before we launch into one-form symmetries? So let me keep up the higher conservation law that I wrote there. And talk about the one-form symmetries of Maxwell theory. So written up there is the conservation law of a general N-form or P-form symmetry current. In differential form notation, a P-form symmetry is associated with a current which is a P+1 form. Here, I'm talking for now about continuous P-form symmetries. We'll do the discrete case soon. So there's a conserved current which is a P+1 form. That's this J up there. And the conservation law can be written as D star of J P+1 is 0. So just as a sanity check for the 0 form case, the ordinary case, J is a 1 form or a vector. Very good. Now, let's focus on the case P equals 1. Yes?
Is there anything preventing us from, instead of using a P+1 form, using E minus just dj equals 0?
Well, that depends on whether you're a person who likes the.
Could you repeat the question?
The question was whether we can. Yeah, the question was whether we can use, we should use the conservation law in this form, or we can just call star of this its own current and then use the fact that it's closed. Of course, these are completely equivalent statements. This is the one that corresponds to J being conserved in the ordinary sense, which is the standard convention. The one you mentioned is the convention in which all currents are closed forms rather than conserved currents. So they're equivalent, but one is more standard than the other. All right. So for the case of one-form symmetries, we are looking for closed two forms, or if you wish, co-closed two forms, which are easily related. And Maxwell theory has two of those. F is closed because of the Bianchi identity, and star F is closed because of Maxwell's equation. So we immediately get two interesting two-form currents, conserved two-form currents. And I'm going to write them in the following form. I'm going to write star J for both of them. So I'm sort of going to have my cake and eat it. I'm going to write the things that are closed rather than conserved. And I'm going to normalize them in a particular way, which will be important for later. So one will be proportional to star F, and one will be proportional to F, but star F will have a coefficient I over E squared in front of it. That, of course, doesn't affect the conservation, but it does affect the units in which the charges are quantized. And here I put a 2 pi for the same reason. All right, so F and star F are closed, so we got ourselves two interesting, potentially interesting, one-form symmetries. Let me leave this as it is for now. So what can we do with those? Well, one of the first things we can do with conserved currents is we could integrate them to get conserved charges. If we do this for an ordinary symmetry with a one-form current that is conserved, and therefore star of it, which is a closed 3-form, then we can integrate that closed 3-form over 3 manifolds to get interesting conserved charges. The analogous thing for 2-form currents, which are closed, is that we should integrate them over closed 2 cycles. That's the only thing we can integrate them over, roughly speaking, since they're 2 forms. So let's do that. Let's follow our nose and define two things that I'll call one-form charges. One is electric and one is magnetic. The first one is the integral of star JE over a surface sigma 2, which for now I'm assuming is compact. And the other one is the integral of star Jm over such a closed two-cycle. Now, the first comment, and the very important comment, is that because these currents are closed, the dependence of these charges on sigma 2 is topological. So if you deform sigma 2 in a way that doesn't encounter any interesting insertions in the path integral, then the difference between one sigma 2 and the other sigma 2 is something where, by Stokes' theorem, you integrate d of this over the cobordism that interpolates between them, and that's 0, because we assume that these were closed two forms. So the dependence of both QE and QM on the surface sigma 2 is topological. And that's not equivalent. That in particular implies that it is a conserved charge in the usual sense, because if it's topological in spacetime, then it's invariant under any deformations of sigma 2, but that includes time translations. Right? Time translations are particular such deformation, so these charges commute with the Hamiltonian. But the fact that they're topological will also have many other interesting consequences. Now, why have I normalized the charges in this particular way with the I and the E squared and the 2 pi? It's so that these integrals of star f and f, when you evaluate them in our conventions, precisely reduce to the standard electric and magnetic Gaussian flux integrals over sigma 2, star f being the electric field, f being the magnetic field. And those normalizations are chosen such that these charges come out to be integers. All right? The fact that these charges are integers in U1 gauge theory will have lots of interesting consequences. But that's why I chose the normalization like this. One small comment. Because of this equation, which is the action of S duality, right, you see that f and star f up to factors change roles. In fact, those factors are precisely the factors that appear in these equations. So you see that the action of S duality exactly, and without factors, maps Q electric, Q magnetic, and Q magnetic to minus Q electric. Very good. Any questions? Let me keep that up. Thing which I say, because we'll mention it later, and I'm sure it'll be mentioned by other people as well, is that using these charges, we can obtain exponentiated topological defects, which are the more standard symmetry defects for discrete symmetries. So let me quickly, because these charges are integers, they generate compact U1 symmetries. And you know from quantum mechanics that the way to get the generator of such a symmetry is to exponentiate the charge with coefficient I theta, where theta is an angle that parametrizes the U1 transformation that you want to do. So we have U1 electric and magnetic one-form symmetries, and the corresponding topological defects that implement the action of those symmetries are the exponentiated. So let me write them. I'll write them simultaneously for E and M. They're parametrized by the surface 2 over which you integrate the charge, and they're parametrized by an angle theta, which parameterizes the rotation that you want to do. It's just exponential with a minus I that I've put here for conventional reasons, and then the angle, and then the charge. So this is precisely the charge that I've written over here. So this is the statement that to every group element in U1, parameterized by such an angle theta, you associate such a topological defect, which implements the action of this U1 symmetry. And the many reasons to do that is because this kind of operator exists even when the symmetry is discrete, even though the currents and the unexponentiated charges do not exist.
So you use the word operator. What are they operating?
I will tell you that in great detail in a second. So I thought you were going to ask about my caveat, which I might have mentioned before you came. So I'm going to use the word operator even though I'm working in Euclidean signature. But there's a more practical sense in which these operate on something, so that they measure the charges of something. And I'm going to discuss that next. Yeah. Very good. Maybe one small comment which I'll make, which is very general, is that because these operators are integrated over only a two-dimensional surface rather than all of three-dimensional space, you can slide them past each other in Euclidean spacetime without them touching. And that means that if you are interested in the commutation relations of these operators, you'll always find that they're abelian. There's no such thing as a non-abelian one-form symmetry. Now here they're U1, so they're obviously abelian, but this turns out to be a very general property. So Greg asked what these things act on or what charges they measure, and that's what I'm going to discuss next. If we were in Lorentzian signature, then these would be actual operators, and we could discuss how they act. In Euclidean signature, the way that such integrated charges act is by linking other things. So that's, for example, familiar from two-dimensional conformal field theory, where if you want to compute the action of the stress tensor on a local operator, you integrate the stress tensor over a curve linking the operator. And so that generalizes as well for ordinary zero-form symmetries. They always link point operators in space-time because they're integrated over codimension 1 surfaces. These things are integrated over two-dimensional cycles, so codimension 2 surfaces, and therefore they don't link point operators. And so here I can make an important comment on what they don't act on. They do not act on local operators. Because again, a local operator would be linked by a 2-cycle. So that means that whatever these things do, there's no local operator that's charged under them. And that actually has important ramifications. We'll see them probably tomorrow, probably not today. The thing that you can naturally link with a codimension 2 surface is a line. So these things naturally act on line defects. And in Maxwell theory, the line defects that carry these electric and magnetic charges are the Wilson and 't Hooft line defects. All right, so let me remind you what those look like. So a Wilson line can be thought of as follows. A Wilson line has two things that it depends on: a charge, Q, which is an integer, and a curve in space-time, C, closed curve. And in Maxwell theory, these are easy to write down. This is just IQE times the holonomy of the gauge curve C. And you can think of this as the quantum mechanical phase, particle of charge E traveling around this curve in space-time. Right. Now, the reason QE is an integer is because we have a U1 gauge field. So large U1 gauge transformations make QE an integer. Right. Now, this is a line in space-time, some kind of loop, if you wish, or you can think of an infinite extended line. So this is a line in R4. If you think of a particular point along that line, you can think of it as a point in R3. In other words, a point charge. You should think of the C as the world line of a point charge. And that point charge, since time immemorial, can be linked by a Gaussian sphere or Gaussian flux surface around that point. And if you compute the integral of the electric field over that Gaussian surface, you measure QE. And this Q that I've defined over here, all the factors, defined in such a way that the QE charge of a sigma 2 that links the line C is precisely the electric charge of the line. That's a small computation that you can in this theory. After all, the theory is free. You probably did it in Lorentzian signature in undergraduate mechanics or E&M or something like that. And if you do the magnetic flux integral, of course, you get 0 because this Wilson line does not carry magnetic charge. By the way, I'll arrive at this result very soon through another kind of quicker path without doing any computation. So that's why I'm not showing you the computation. All right, so that's the electrically charged line. What's the magnetically charged line? The magnetically charged line is called a 't Hooft line. Let me write it over here. And a 't Hooft line represents the effect of a very heavy non-dynamical magnetic charge, probe charge, traversing the curve C. So we'll denote the 't Hooft line by H. It's labeled by the magnetic charge and by the curve C. Now, in the original presentation of Maxwell theory, I cannot write such a simple, yeah.
Should that have been QM?
Absolutely. Whatever I did, it should have been QM. Third time's the charm. All right, QM. So in the original presentation of this theory, it's not so easy to define what this object looks like. This object, you should think of it as being analogous to the winding operators of the compact boson, which are disorder operators. Similarly, the 't Hooft line in the standard presentation is a disorder operator. In order to define it, you focus on a small point on the line, which again is a point in R3, if you wish. And then you drill a small hole or small sphere around that point, and you put a Dirac magnetic monopole on that small sphere. And then you take the limit of the sphere becoming very small. So this is the world line of a singular Dirac magnetic monopole. However, it is much easier to describe in the dual presentation of the theory, because there it is just the Wilson line of the dual gauge field A tilde. So that's one way of defining it. And since it's much easier, that's what I'm going to write. These are, of course, equivalent. And because this line, by definition, has a Dirac monopole of charge QM on its world line, when you evaluate the magnetic flux integral over a sigma 2 that links this line once, for example, this S2 links the line once, if it's a standard Gaussian surface, then this QM is literally just the QM that I put here. All right, so we have Wilson lines which are charged under the electric symmetry. We have 't Hooft lines which are charged under the magnetic symmetry. And of course, we have fusion products of all these lines. In other words, we have arbitrary lines of electric and magnetic charge. These are called in general dions. And they carry the corresponding charges. Now, one small comment that I'll make now, maybe that'll become much more important tomorrow, is the fact that while the Wilson line and the 't Hooft line, the way I've defined them, are both bosons, they have bosonic statistics. In other words, if you compute a tangle of lines that represents the two particles going around each other by a 2π rotation, then they behave as bosons. You don't get any sign. But some dions, in particular the dion of electric and magnetic charge 1 and 1, have Dirac angular momentum. And therefore, they behave like fermions. So if you take the 1,1 dion and you do the same computation, you get a minus sign. And the fact that some lines can be bosons and some lines can be fermions is very interesting, and it'll play an important role tomorrow. All right. Oh, another important comment that I want to make, because this is another way that people sometimes characterize one-form symmetries. So here we have characterized them through conserved charges, right? The electric and magnetic fluxes. Now, there's an implication of this conservation law. Since these are curved, it means that the lines that are charged under them, namely the Wilson and the 't Hooft line, cannot possibly end. Because if they did end at some point, just terminate the line at some point, then you could take this charge operator, which after all we declared was topological. We didn't just declare, we checked it. And then you slide it off the end of the line, and then there's nothing there that sources the electric or the magnetic flux. And so you just get 0. All right. So in a theory that actually has this flux conservation symmetry, or one-form symmetry, as an exact symmetry, the corresponding charge lines cannot end. Conversely, if there are things that the lines can end on, then form symmetries are broken, either completely or to an interesting subgroup. And that's one of the more intuitive ways of thinking about one-form symmetries in various contexts. I'll mention that again tomorrow when we add charged matter to these free theories, but I wanted to mention it now as well. Questions? Yeah.
QE sigma 2 equals to small QE. Do you mean like when you act on the Wilson line, you get small QE?
Yeah, so both on the left side and on the right side. The more precise way of writing this is to write the Wilson line on both the left and the right of this equation. In other words, if you have the Wilson line and you link it with the surface, then you get the Wilson line times QE. Right. Was that the question?
Yeah.
Good. Other questions? Yeah.
Usually when we talk about S duality, like the coupling, we send coupling to tau to like -1 over tau.
Uh-huh.
But there we see that E squared, like E total square is going to like 1 over E squared. Is there a missing minus sign or?
No. What is tau? Tau is I over E squared. Tau is complex. E is the imaginary part of tau. When tau goes to -1 over tau, the imaginary part of tau does exactly what I said E does. So there's no problem. There's no missing minus sign. E squared is always but indeed, that is the correct way of writing it. And in the case of no theta angle, there's no real part for tau. Tau is purely imaginary, and it's proportional to I over E squared. So you can check that your formula and my formula do the same thing. All right. Let me see how much time I have left.
It's about 19 minutes.
OK, great. So the thing that I want to say next, talk about next, is to situate this free theory and its symmetries in the context of phases of gauge theories. All right? And I'm going to start by the sort of most traditional way of characterizing phases of gauge theories, and then I'm going to tell you how it's related to one-form symmetries. So if you read many nice reviews and textbooks, you'll read about how to characterize phases of gauge theory by thinking about the effective potential between two heavy probe charges. All right, so imagine that you have a heavy probe charge Q. It could be Q electric, it could be Q magnetic, it could be a quark in some non-abelian gauge theory, whatever. So you can have Q, and then there's its CPT conjugate Q bar, right, which is its antiparticle, if you wish. And you can ask, imagine Q and Q bar are very heavy, so they don't fluctuate. They're just probes. And you separate them by some distance r. You could ask, what is the potential energy between Q and Q bar? This is called the static Q bar potential. It's a very famous quantity. And different behavior for V characterizes different kinds of gauge theories. So the thing I want to start with is, how does this V look like in Maxwell theory? And how is this related to one-form symmetries? All right. So in Maxwell theory, you can take Q to be either an electric charge or a magnetic charge. If you're sophisticated, you could do it for a general dion, but I'm not that sophisticated. So let's do it for an electric and a magnetic charge. If Q is an electric charge, then this formula is painfully familiar. This is minus E squared Q electric squared over R This is the Coulomb potential between electric charges in conventions in which Q is an integer and the gauge coupling is E. So in normal physics, you call Q times E the charge of the electron, for example. And you can do the same thing for magnetic charges. Easiest to do in the dual presentation. You get exactly the same formula, except that E becomes E twiddle, and Q electric becomes Q magnetic. And of course, E twiddle is 1 over E, or 2 pi over E. So both electric and magnetic charges obey Coulomb law. And for this reason, Maxwell theory, or indeed any theory where these formulas are true, is said to be in a Coulomb phase. Now, in the context of what I said before about Landau's paradigm linking the realization of symmetry to the classification of phases and phase transitions, we should ask ourselves whether this notion of Coulomb phase can be captured by something about the one-form symmetries. So that's what I want to explain now. And I'm going to switch to a seemingly unrelated question. The seemingly unrelated question is whether or not the one-form symmetry is broken or unbroken in Maxwell theory. So, oh, wait, I'm going to need the formulas. Thanks, that's helpful. I'm going to keep this formula because I'm going to have to say something about it in just a second. So here's a quick and dirty way to see that both one-form symmetries need to be spontaneously broken in Maxwell theory. These are the charges. They're integrals over F and star F. F is a free field. When we act with these charges on the vacuum, F creates, and because you integrated it, it might be a photon of very low or zero momentum, so that is some sort of non-normalizable state. The fact that the charges don't annihilate the vacuum is already a signal that the symmetry is spontaneously broken. But even more than that, they create a one-photon state. And what does that remind you of? Goldstones, right. So the photon is the Goldstone boson for the spontaneously broken one-form symmetries. And in fact, here there are two one-form symmetries, electric and magnetic. They're both spontaneously broken. And the photon has two polarizations, which precisely accounts for that fact. All right, now let's do the more sophisticated version. The more sophisticated way to answer whether or not a symmetry is spontaneously broken is to ask whether there's any operator O that carries some charge under it that gets a VEV. And for normal symmetries, this O is a local operator. We can either ask whether O gets a VEV, or equivalently, slightly more sophisticated thing you can do is to take O dagger at X, O at Y, and if you separate O dagger from O by a very large distance by taking X and Y very far apart, then by clustering, this thing will go to the VEV squared of O. So by looking at the long distance behavior of this two-point function and seeing whether it goes to 0 or to a finite constant, you can diagnose whether O is VEV and whether the symmetry is broken or not. There's an analogous criterion for lines and one-form symmetries. So the analog of this OO dagger, there is an analog of this for lines as well, but I don't want to talk about it because it's a little bit unusual and it makes more sense in Lorentzian signature, blah, blah, blah. This has a very nice analog for lines. So the analog of this O dagger O correlator is a big line, a big loop, L along some contour C. L could be a Wilson line, a 't Hooft line, a dion, it doesn't matter. And then you take the loop and you make it very big. That's the analog of sending X and Y to infinity here and separating them by a long distance. So when the loop becomes big, which I'll schematically denote like this, then you can ask, what does the expectation value of this line do? Does it go to 0? Is it finite? Does it mean that there's symmetry breaking or not? Since we already concluded that there's symmetry breaking, we better find that there's some loops that have an interesting expectation value. All right. And the way the loop is taken to infinity is not so important, just as it wasn't so important how exactly you took X and Y to infinity. As long as they're far enough apart, then clustering will kick in. So you could take it to be a large circular loop, a large square loop, a large rectangular loop. As long as you scale it up uniformly, you're fine. All right. Now, there's a small comment I need to make. I'll make it briefly, which is that just like local operators can be rescaled by something like wave function normalization, loops can be rescaled as well. And they can be rescaled by local counter terms living on the loop. And those are the analogs of wave function renormalization factors for loops. And the simplest loop counter term is a counter term that simply involves the perimeter of the loop, which is the integral of ds, the length of the loop. Greg can't see, sorry. Right. So this is a local counter term on the loop. It's basically the cosmological constant on the loop. And it modifies the expectation value of the loop by a term that in the exponent, which is proportional to the perimeter. And the coefficient is some mass scale, which you can think of as some kind of mass renormalization for the heavy probe quark that you're discussing, or probe particle. All right. There are other counter terms as well, but they won't contribute to the discussion that we're about to have. You need to be mindful of the fact that when you ask expectation value of the loop 0 or non-zero or 1, you have to deal with this potential renormalization ambiguity. Very good. This renormalization ambiguity modifies the loop by something that looks like e to the minus m, where m is some mass scale times the perimeter. Okay. Now, we want to ask whether L has a finite expectation value when the loop becomes large. But because of this ambiguity, you see we need to qualify what we mean by finite. Because if the sign here is negative, it can have either sign. But if the sign here is negative, then the perimeter will still decay at long distances. So it might look like the loop goes to 0, but that's imprecise. You should ask whether there's a scheme in which you can sort of remove this counter term, and then there's a sensible notion of VEV to be non-zero. So in other words, we say that the VEV of the loop is non-zero if and only if thing scales like some constant times perimeter. This is called perimeter scaling. It's very famous in QCD in particular, but in all of this world. And whenever you have a loop that has perimeter scaling, then it means that the loop has a non-trivial VEV, a non-zero VEV. One way of saying that is that you can then renormalize the loop, if you wish, by rescaling that perimeter term to 1. And then it just has a constant VEV, which is the standard symmetry breaking VEV. Now, let me briefly relate this to the QQ bar potential over here. The perimeter counter term just shifts the potential by a constant. So this is the standard statement that the potential doesn't have a natural 0. OK, very good. Now, depending on how much time I have left, so will or will not say this. Yeah. So now let's try to relate what we said about the QQ bar potential over here to the VEVs of large loops. And I said before that I can take the loop to be anything I want. So let me take it to be, as is often done in Euclidean gauge theory, a large rectangle. Here's my loop. It doesn't matter so much what I do at the corners, so don't worry about the singularities. And I'm going to take the loop to have length r in this direction, length t in this direction. You should think of this as Euclidean time. And here's my loop, right? And you can think of this line here traversing the loop in the upward direction as the line that sources the charge q. And then on the other side of the loop is oriented downwards. So we have a particle going backward in time, and that is the corresponding antiparticle q bar. So the expectation value of this loop is the amplitude for a QQ bar pair to form, be separated by a distance r, travel t in time, and then come back and be annihilated. So what I've just described literally is the statement that the expectation value of this loop, this large rectangle, we call it rectangle, is e to the minus t times the QQ bar potential, up to perimeter counter terms. Great. Now we're in business. all the loops, all the static potentials here have Coulomb scaling. So V goes to 0. If I take into account the fact that V could go to a constant, then it goes to a constant. Okay. So V goes to 0 up to a perimeter counter term, and therefore every single loop, has perimeter scaling and therefore a VEV, not VAV. Good. So that means that the U1 electric and U1 magnetic one-form symmetries under which these loops are charged are completely broken. The argument with the photon, roughly speaking, told us that the continuous part was broken, but here we see that there's even a discrete part left over because every single loop has a VEV. If there were a loop that had 0 VEV, then some discrete subgroup might have been unbroken. We'll see examples of that tomorrow. Very good. Any more questions about this?
Actually, I have like about this loop.
Sure.
Because you were saying that like I can think of the two sides as like expressing Q and Q bar.
Mm-hmm.
But like, what is the kind of the point of creation of the two? So like they are like spatially separated.
Well, if you want to deform the loop slightly so that it doesn't have edges, then you can think of them as being pair created here.
Is there an interpretation when the line is inserted in a spatial?
Well, then you'll have to deal with it. So if you have an act at one instant in time, then so roughly speaking, if you pair create them at the point, then there's no electric flux anywhere. And then as you separate them by a distance r, you'll pull them apart against the Coulomb force, and you'll create the effective flux that sources the Coulomb field. If you just act with a line at a fixed instant in time, then essentially that's the creation operator for the entire electric flux happening in one go. So it achieves the same outcome, but it happens in one instant rather than through this dragging of Q and Q bar.
Do you have interpretation? Because here I have like this nice interpretation of
it's the electric flux. Right. I mean, this operator, the operator A is conjugate to the electric field. So if you act with this operator on the vacuum, you create electric flux. That's the interpretation. Yeah. Sorry?
How do you calculate the expectation value?
So you mean how do you get this formula? Well, so if you allow me to ignore the niceties about what we just discussed, and you just focus on this part of the loop. Imagine it extends for a really long time, which is the thing we're looking at here. Then we're looking at a situation in Euclidean space where we have a loop going up and a loop coming down. And if we cut this system in Lorentzian signature, where we have a positive and a negative charge defect at these 2 points. And what we're computing is literally the time evolution amplitude, the propagation amplitude of this system. In Lorentzian signature, that would have an I. In Euclidean signature, it's just e to the minus t times the Hamiltonian of this loop pair. I could H if you wanted to, but it's conventional to call this the potential since it's time independent. The loops are not moving around. They're just sitting there in space, so this is a time independent energy. Yeah?
Does the coefficient of the perimeter term matter?
No, it does not. That's exactly what it means that you can change it by a counter term. So the fact that you can add a counter term means that if two different people do the same computation, this computation, using two slightly different definitions of the loop, then their answers might differ by such a counter term. And what this tells you is that loops are not the same. Loops are operators, right? They're not physical probe particles. If you had a physical particle, it would have some mass, and it would be sensible to ask what is its mass and so forth. But for the probe particle, the mass is kind of infinite to start with, and it's not really sensible to ask what is the mass of the heavy probe quark. In fact, because this coefficient is dimensionful, it's dimension 1, you would typically expect it to be infinite, proportional to the cutoff. So it's a scheme-dependent ambiguity, And therefore, the continuum or the universal part of the theory doesn't distinguish between these things. Other questions? Maybe since I don't have time to say anything else or start a new topic, I'll very quickly mention an alternative way, a very nice alternative way of getting to this answer. This is the answer that every loop has a non-zero VEV. Here I use the rectangular loop because it's very nicely related to the static potential. That's always true. In any theory, you can discuss this rectangular loop, and it is the static potential. However, in certain theories, the static potential also shows up in other loops. For example, in this theory, which happens to be a conformal field, the circular loops also know about the static potential. And the reason for that is that you can show, as was done long ago by Michael Peskin, that in a conformal field theory, the static potential always looks Coulombic, always looks like 1 over r, with some coefficient which is a pure number. Here are the numbers for Maxwell theory, but it could be some interesting number. For example, in n equals 4, some finite coupling, those would be interesting numbers that depend on the coupling. And using conformal symmetry, you can show that the expectation value of the loop is the exponential of this number. And in particular, it is non-zero. So that's a fast, very slick way of getting the non-zero expectation values of the large circular loops without doing an explicit. Yeah?
So when you say every loop has a VEV, just to clarify, this is every contractible loop?
Well, I think what the more precise way of saying it.
Could you repeat the question?
The question was whether every when I said that every loop has a VEV, I mean every contractible loop. It's actually a little bit more subtle than that. The things that have genuine VEVs, like the analog of the question of whether just O has a VEV, are not contractible loops. And the reason for that is that a contractible loop doesn't actually carry any under the one-form symmetry. We'll see that explicitly tomorrow. It's a little bit, it's not obvious based on what I've said. But here's an intuitive argument. If you have a contractible loop, then you can write it as an integral of f or star f over a two-dimensional sheet bounding the loop. So roughly speaking, it comes from integrating a local operator, and therefore it doesn't carry one-form charge. I'll show that explicitly tomorrow once I introduce background.
I thought the point of your argument showed that
Hold on, I'll explain in a second what I actually showed. What I actually computed was the analog of this. You see, this operator, O dagger O, also doesn't carry the U. Imagine O is charged under standard U1 symmetry. Then the correlator O dagger O is also neutral under that symmetry. Nevertheless, when you compute the two-point function, very long distances, and you find that it's non-zero, then by clustering, you conclude that the actual one-point function is also non-zero. So what I did is the analog of that. I computed the expectation values of large closed loops, and then concluded by clustering that the thing that is actually charged under the symmetry has a VEV. Now, the thing you should ask me is, what is the thing that's actually charged under the symmetry? What's the analog of O itself? The analog of O itself is a non-contractible loop. But in flat space, there are no non-contractible loops. So what am I talking about? The correct notion of non-contractible loop is a loop that goes all the way to infinity, that is open and goes all the way to infinity, and that connects different points on the boundary. So that doesn't look non-contractible topologically, but because of the way we impose gauging at infinity, that loop piercing the Gaussian surface at infinity deposits charge there.
So it would have a zero VEV.
A non-zero VEV.
What about selection rules?
If the symmetry is spontaneously broken, there are no selection rules. If the symmetry were unbroken, then every charged operator would have zero VEV. The signal of spontaneous breaking is that a charged operator can have a VEV. Any other questions?
By taking t to infinity is not more or less this what you're doing, like kind of considering two loops that go to infinity? Not loops, but...
Well, this big square.
Yeah.
Yeah, right, exactly. So you should think of this as kind of pinching, right? So so for operators, the way that clustering works is that I take an O and an O dagger, and I just move them far apart. And then they factorize into VEV of O and VEV of O dagger. If I take a very large loop, you should, roughly speaking, imagine that once this large loop sort of hits infinity, it pinches off into different little bits that look like the kind of charged things I was describing. So the claim is that a non-zero expectation value for these large loops is tantamount to having these lines that go to infinity have non-zero VEV. But those are much more subtle to deal with. directly.
Can you also have like operators insertions that create kind of a non-trivial topology, like even in flat space?
Well, yes, absolutely. So there's two ways you can get non-trivial topology. One is by just putting it in by hand. Say you just declare that you're studying the theory on an interesting manifold with 1 cycle, 2 cycles, blah, blah. Or, alternatively, you can create the topology using defects themselves. For example, when you insert a loop, right, because the loop modifies what's going on there, right, roughly speaking, because the loop requires renormalization or regularization. That was most obvious for the 't Hooft loop. You can kind of think of this insertion as drilling out a small tubular neighborhood from the spacetime. So that effectively the spacetime with defect insertions has non-trivial topology. And that's how loops can link with each other and so forth, and you get interesting answers, even though the spacetime manifold itself looks trivial.
All right, well, let's thank Thomas for a very nice talk. Before we break, I just want to remind everyone that tonight is the barbecue at the WeatherTech Cafe at C4C at 6 p.m. If you're planning on drinking alcohol, please bring your ID. And Thomas, it's his first day. Unless he has other lunch plans, show him where the C4C is so he can eat. And ask him more questions there.